All right, these are the solutions for rotation 5. So we've got a wheel with a moment of inertia of 500. We want to know the rotational kinetic energy if it's rotating at this speed. So, simply put, the rotational kinetic energy is 1/2 I omega squared. So 1/2 times 500 times 25 radians per second squared gives me a rotational kinetic energy of something huge, 156,250 joules. So all we've got when we're talking about rotational kinetic energy is a new way to calculate kinetic energy. This happens to be, anytime something's spinning, we're going to have this kind of energy. So, what is the angular velocity when it has this many joules of rotational kinetic energy? So, in this case, K is 1/2 I omega squared. We're going to solve for omega here. That's 2K over I square rooted. So it's the square root of 2 times our kinetic energy, 2.25 times 10 to the 5th joules, divided by the rotational inertia of 500. We put that in, it comes out to be 30 radians per second. With these two problems, we're just looking at how the formula is put together. Nothing more than that. Okay, so a wheel has this mass, this radius, and it rolls such that the center of mass has a velocity of 10 meters per second. I want the angular velocity of the wheel, K. So in this case, we're rolling without slipping. This means that we can assume that the angular speed of the wheel is equal to the velocity divided by the radius. That's going to be important. So the angular speed of this wheel is going to be the velocity of 10 meters per second divided by the radius of the wheel, 0.25 meters. And so this angular speed comes out to be 40 radians per second. Calculate the translational kinetic energy of the wheel. Translational kinetic energy is that linear kinetic energy that we have. It's just 1/2 mv squared. So 1/2 times our mass of 0.5 kilograms times our velocity of 10 meters per second, whole quantity squared. So when we get that, our linear kinetic energy, our translational kinetic energy is 25 joules. The rotational kinetic energy is 1/2 I omega squared. So we have a wheel, so that's 1/2 mr squared times omega squared. So 1/2 times the mass of my wheel, 0.5, times the radius of the wheel, 0.25. That quantity is squared. That's the mr squared part, times omega, which is 40 radians per second squared. So when we plug in all of our numbers for that, our rotational kinetic energy also comes out to be 25 joules. And if I want the kinetic energy of the wheel, it's both of those things put together. So if something is rolling without slipping, its energy is a combination of linear kinetic energy and rotational kinetic energy. So the total kinetic energy is going to be 50 joules. So number 5, we have a solid spherical marble. It's in a projectile launcher. And this is the spring constant. We're going to compress it and we're going to fire it out. So if it's not rolling, here's what we're going to look at. We're going to look at an energy diagram of what's going on. This is before we fire. If that's the case, before we fire, all the energy we have is spring potential energy. And then we're going to look at the energy after. So all of that's going to become kinetic energy. But if we're not rolling, that means there's no spin to the wheel. That's going to be all linear kinetic energy. And so what we have is all of that spring potential energy turning into linear kinetic energy. So for a spring, it's 1/2 kx squared is equal to just the linear kinetic energy, 1/2 mv squared. So my velocity is going to be the square root of kx squared over m. So my velocity comes out to be the square root of 1,000 times, what are we saying? That's the radius, sorry. It's going to be 1,000 times 0.25 meters squared divided by the mass of my object, 0.2 kilograms. So that velocity is going to come out to be 17.7 meters per second. Now, if the marble rolls without slipping out the launcher, we're still going to look at the before energy. We got spring potential, got a whole bunch of that. But after, if it's rolling without slipping, I'm going to have linear kinetic energy and rotational kinetic energy. I'm sharing between the two. I don't necessarily know the ratio just yet, but I know we're going to have less linear kinetic energy, so we should have less velocity as a result. All of that potential energy is not going into making the thing move forward. Some of that potential energy goes into making it move forward, and the rest of that energy goes into making the thing spin. If that's the case, I have less linear potential energy, which means I have less speed. So in this case, all that spring potential energy turns into linear kinetic energy plus rotational kinetic energy. So 1/2 kx squared is going to turn into 1/2 mv squared plus 1/2 I omega squared. Now, if I want to be able to get the velocity, what I have to do is substitute for I and for omega. For a sphere, the I is 2/5 mr squared, and omega is always v over r. So we're going to put those two things in there. We got 1/2 kx squared equals 1/2 mv squared plus 1/2 times 2/5 mr squared times v squared over r squared. We're going to end up squaring both of those because it's omega squared. So these r squareds go away, and I've got 1/2 kx squared equals 1/2 mv squared plus what we have there is 1/5 mv squared. And so we can start combining like terms if we want to. 1/2 kx squared is equal to 1/2 plus 1/5 is 7/10 mv squared. We're getting there now. Multiply both sides by 10/7, divide by m, and we get our velocity to be the square root of 10 over 14 times kx squared over m. Plugging in all of our numbers, we end up with 14.9 meters per second. Now that's a lot of work to get to our answer. I do expect you to do that kind of work. But if you'll notice, one of the things we said before we even started was that because we have less linear kinetic energy, we're going to have less velocity. And that's exactly what we see. So now to get into something a little bit more complicated, and we'll talk about part B. So we're going to send a block up this incline. If we look at this block going up the incline, we're going to start down here. So let's look at the energy at the bottom. The energy at the bottom, this is just a block, is all linear kinetic energy. I'm going to make that a little smaller. So the energy at the bottom is all linear kinetic energy. And that's all that we have going on. Now, in part A, we'll look at the energy at the top. All of that linear kinetic energy is gone, and it's going to become potential energy. So in this case, I have linear kinetic energy becoming potential energy. So all the energy at the bottom, linear kinetic, is equal to potential energy at the top. So 1/2 mv0 squared is equal to mg, and we're going to call that capital H. So if we want to find out what that height is, we got to solve for it. The m's cross out, and so that height comes out to be 1/2 v0 squared over g. That's our height, and we want to keep this in mind. Now, I'm modifying this question for you. Determine the maximum height to which the block will rise. And I want to ask, will the block rise to H or not? And then I want you to tell me why. So if you've already answered that part, pause and change to that. Will it make it to h? Will it go less than h? Will it go greater than h? And why? So if we look at the top in this case, because there's friction, if there's rough, if we have a coefficient of sliding friction, anytime we have sliding friction, we're going to get a byproduct of heat. So instead of having all of my energy as gravitational potential energy at the end, some of it's going to be the work for friction. And if we look at this, the linear kinetic energy we had at the beginning is going to be equal to gravitational potential energy at the end plus the work done by friction. This is going to be the same. It's going to be split in between these two. So we're going to have less potential energy, which means less height. We're not going to make it to h because some of our energy is lost to friction, is lost to heat because of friction. I didn't really want to get into that calculation. It's a little too complicated for this course. All right, now we're going to take and swap out the block, and we're going to go to thin hoop. And we're going to say the hoop has translational velocity and rotational velocity. It's rolling up the ramp. So we're going to look at the energy at the bottom. We have linear rotational energy and kinetic, linear kinetic energy and rotational kinetic energy. Now at the top, because we're rolling without slipping, we know that once we get to the top, the linear energy is going to be 0. But if we're rolling without slipping, those two are related. So anytime we get to rolling without slipping, V is equal to R omega. So if we get to the top and we stop moving, stop sliding forward, then omega also has to be 0 because those things are related. So I don't have any more rotational kinetic energy. And I know I'm going to have gravitational potential energy. I'm also not going to have any work done by friction. The reason I'm not going to have any work done by friction in this case is because, and we'll write this in red kind of above. I only get heat lost to friction. I only get this work done by friction from kinetic or sliding friction. If it's rough and we roll without slipping, then there is no work done by friction that's taking away the energy from my system. So at the end here, all of my energy is gravitational potential energy. What this means as far as what's doing work to make things happen, for the linear energy, gravity does work to turn the linear kinetic energy into gravitational potential energy. That's normal. That's what happened in part A. But here, friction's doing something different. In this case, what we have is friction is doing work in this case, but it's not being lost to heat. The work that friction does becomes gravitational potential energy. That's sort of the advantage to having friction when this thing is rolling. So all of my linear kinetic energy and all of my rotational kinetic energy become gravitational potential energy. So 1/2 mv squared plus 1/2 I omega squared is equal to mgh. Both of those are going to contribute. So even before we go into this, I'm going to have more height at the end here because I have more energy I can put into gravitational potential energy. So 1/2 mv squared plus 1/2, and this is a wheel, this is a hoop, so mr squared, and then omega squared is going to be v squared over r squared equals mgh. So the r's all go away, the m's go away, and I've got 1/2 v and the m's, sorry, 1 half v squared plus 1 half v squared equals mgh. That's just v squared equals mgh. So my height here is v squared over g. That's twice the height that we had before. I have twice as much energy now because of this extra term that can turn into gravitational potential energy. Now, next part is if the incline is frictionless. So let's start off looking at our energies. At the bottom, we have linear kinetic energy and we have rotational kinetic energy. That doesn't change. We're still spinning. But at the top, gravity is still in my system. So that means gravity is going to allow all of that linear kinetic energy to turn into gravitational potential energy. But there's no friction. If there's no friction, then this is not going to happen. I don't have friction to change rotational kinetic energy into gravitational potential energy. So I still have the same amount of rotational kinetic energy at the end. So what we're going to do here as far as our conservation of energy is to say the energy at the bottom, linear kinetic energy plus rotational kinetic energy, is equal to the energy at the top, potential energy plus rotational kinetic energy. These two things are the same, so that's gone. So linear kinetic energy turns into gravitational potential energy. There's no change in the rotational energy. When that ring goes up, it's spinning at the bottom, and because there's no friction, it's spinning at the same rate at the top. It slides the whole time. So 1 half mv squared is equal to mgh. My m's go away, and the height here comes out to be 1 half v squared over g, which is the same height that we had in part A. All right, that's what we've got for today.